Greetings to everyone. So today we are going to discuss about the problem which are related to design of beams. Okay. So last two classes we have discussed that the beam with concentrated load. Okay. So today we are going to have the design of beam with UDL. Okay. So let us move on to the problem. So the problem is a simply supported beam laterally supported of span 10 meter. So simply supported beam laterally supported of span 10 meter carries an UDL of 60 kilonewton per meter. 60 kilonewton per meter. Design the section and check the section for shear and deflection. So we can go for two things. That is UDL. Along with the UDL, we can have point load. Okay, central point load, kilonewton meter. In addition to the UDL, so in addition to the UDL, the beam has the central point load of 40 kilonewton. 40 kilonewton. Design the beam. Design the beam and check the section for the shear and deflection. Check the section for the shear. So here they restricted that check the section for shear and deflection. So only these two things is enough for completing the problem. Okay. So given data. So the given data is the beam is laterally supported and it is simply supported, has the span of 10 meter. So L is equal to 10 meter and it have the UDL of 60 kilonewton per meter and the central point load of 40 kilonewton. So 5 meter and 5 meter. Okay. So A, B, and C. So now we have to do the design. Design the beam. So let us move on to the solution part. So the step one is to calculate the shear force and bending moment of the section. Of the beam. Okay. So there are two things. One is point load and the another one is one is UDL and the another one is central point load. So L equal to 10 meters here and the W is equal to 60 kilonewton per meter. So RVA1 here RVA2, RB1 and RB2. This is 40 kilonewton acting at a distance of 5 meter and 5 meter from the each support. Now I have to calculate the value of RA1, RA2. Therefore, RA becomes, okay, addition of RA1 plus RA2. Okay. Similarly, RB is equal to RB1 plus RB. Mostly both are same. RA is equal to RP. Okay. So let us have the calculation part. So the total load. So here take moment about A. Take moment about A. So RP1 into 10 minus 60 into 10 into 10 by 2. Okay. Is equal to 0. Therefore, RB1 is equal to 60 into 10 into 5 divided by 10. So it becomes 300 kilonewton. Similarly, here take moment about A. So RB2 into 10 minus 40 into 5 is equal to 0. Therefore, RB2 is equal to 40 into 5 divided by 10 becomes 20 kilonewton. Therefore, total load, total shear force, okay. So 300 plus 20, it becomes 320 kilonewton. So RA is equal to RP, so total reaction is equal to 320 kilonewtons. Okay. So now we have to go for the moment. So that for the next section we can go. RA is equal to 320 kilonewton and RB is equal to 320 kilonewton. Okay. Now we have to calculate the moment at C. Moment at C. So MC is equal to the maximum moment MC is equal to RA into 5 meter minus 60 into 5 into 5 by 2. Okay, with respect to point C and calculate. Okay, so RA is equal to 320 into 5 minus 60 into 5 into 5 by 2 becomes 750. Therefore, moment at C is equal to 320 into 5 minus 750 becomes 850 kilonewton meter. 850 kilonewton meter. So this is the maximum moment. Okay. Now what should I do? We have to choose the selection with respect to the moment. Okay. So step 2, calculation of ZP required. That is the required section modulus. Okay. ZP required. So for that we have the formula, that is M should be less than MD condition. So this is after selecting the section we have to do. So M is equal to, so MD we have the formula, which is nothing but beta B into ZP into Fy by gamma M naught. Whereas Fy is equal to 250 Newton per mm square and the beta B is equal to 1 for plastic section and the gamma M naught is equal to 1.1 from 35. Okay. So next MD I'm going to take as MC or M, which is equal to 850 kilonewton meter. 850 kilonewton meter. So 850 into 10 to the power 6 Newton mm. Therefore, if I'm going to substitute into the above equation, okay, then I can calculate the ZP requirement. Okay, so 850 into 10 to the power 6 into 1.1 divided by 250 becomes 3740 into 10 cube cube. So this is the ZP requirement. So now I have to select a section. Okay, select a section. How ZP is more than the above, more than the above requirement. Okay, so let us move on to the code book. So sorry, steel handbook. Okay, so steel handbook will be, I will take the steel handbook. So I will share the handbook for you. For your reference, I am sharing the handbook. So for reference, I am sharing the handbook. So in the handbook, we have to select an I section, which is, sorry, which have the ZP value more than 3740. That is our requirement. So here the I section and the Z value is available here. So here I have to select a section which is based, the value is more than 3000 something. So here only one section is available, that is ISWB 600. So 3854.2. Okay. So under ZX well. So the ISWB 600 have the Z value of 3854.2 into 10 to the power 3 mm. So that section may be suitable for our requirement. Okay. So let us write the requirements as per ISWB 600. Okay. So our requirement is available like this. Let us move on to the selected section. So select this section. Select I section of ISWB 600. So their properties are total height H is equal to 600 mm. Okay. Breadth of flange BF is equal to, in thickness of flange TF is equal to, thickness of Z TW is equal to, then H2 is nothing but the distance from toe to edge, from here to here, or if it is here, will be called as H2. This distance we have to calculate now. Along with that, we have to go for IXX value and the ZXX value. So ZXX is 3854.2 into 10 to the power 3 mm cube. Okay, from the steel handbook. From Steel handbook. Okay. Now remaining values we have to 54.2. This is then H2 value is 46.05. H2 value is 46.05. 46.05 mm. H2 is equal to 46.05 mm. So next, depth of flange. So width of flange is 250 mm. Thickness of flange is 23.6 mm. So 250 mm and 23.6 mm. Next, thickness of web. So thickness of web is equal to 11.8 mm. So thickness of web is equal to 11.8 mm. Then IXX value is equal to 1,15,626. 1,15,626.6 into the power 4 mm power 4. Then R minimum is equal to 5.35 mm. R minimum, the least value is 53.5 mm, the least value. Okay? So these are all the values corresponding to our section. Okay. Now let us move on to the thing. That is Z required, ZP required should be less than ZP provided. Okay. Now we have the condition that M should be less than MD, whereas M is equal to 850 kilonewton meter. Okay. But MD we have to calculate, that is beta B in the reverse manner. ZP provided multiplied with Fy divided by gamma M naught from page number 52 of IS 800 2007. Okay. So here beta B is equal to 1. ZP provided is equal to 3854.2 into 10 to the power 3 multiplied with 250 divided by 1.1. If I'm going to substitute this, the moment capacity of the section will become 879.95. So 878 point, sorry, 875. The answer is 875.955 kilonewton meter. So M is less than MD. Hence, safe in bending moment transfer. Okay. So here it is safe. Next, we should move on to shear force calculation. Okay. That is check for shear. So step 3, check for shear. So we have the condition from page number 52. That is, V should be less than 0.6 times of VD, whereas VD is equal to, the formula will be available in page number 59 of the code book. So VD is equal to Vn by gamma m naught, whereas Vn is equal to Vp. So Vp is equal to area of web multiplied with Fyw divided by root 3 into gamma m naught. So this is the formula for Vp. Whereas area of web, so height of web multiplied with thickness of web, which is nothing but height of web I am going to take as 600 mm, and the thickness of web from the diagram it is 11.8 mm. So 11.8 mm. So then the area is equal to 600 into 11.8 becomes 7080 mm square, and Fy is equal to 250 Newton per mm square, and the gamma m naught is equal to 1.1 from table 5. From table 5. Therefore, Vd is equal to, so 7080 multiplied with 250 divided by root 3 into 1.1 gamma m naught. So it becomes 929.009 kilonewton. Therefore, 0.6 times of Vd is equal to 557.405 kilonewton. So here, how much shear has been developed? 320 kilonewton is developing from the support, but the section can withstand 557. Therefore, V should be less than 0.6 times of VD. Okay. Hence, safe in shear transfer. So the section is safe in shear transfer. Next, check for deflection. Check for deflection. So check for deflection. So we all know that delta should be less than delta limitation. Okay. So if the delta due to UDL plus delta due to point load is equal to how much, that we have to calculate. So delta due to UDL, if the formula is 5W L power 4 divided by 384 EI. Similarly, delta point load is nothing but WL cube divided by 48 EI, whereas W is equal to working load. Okay. So if it is working load, then we have to convert divided by factor of safety. Okay. So the UDL is equal to, working load is equal to factored load divided by factor of safety. So I'm going to take the factor of safety value as 1.5. So here 60 divided by 1.5 is equal to 40 kilonewton meter. 40 kilonewton per meter. Similarly, for point load, PL is equal to 40 divided by 1.5. So it becomes 26.67 kilometer. Then we know that E is equal to 2 into 10 to the power 5 Newton per mm square. Okay. So we are going to assume the value so that L is equal to, they have given us 10 meters, so 10,000 mm. Okay. So I value we got that from the steel handbook, 1,15,626. 1,15,626.6 into 10 to the power 4 mm power 4. So substitute in this formula so that we can get 5. The answer becomes 22.5. 22.5 mm. Here, so here it is 2.40 mm. So we have to check that value also. Okay. So the combined together, the answer is total delta is equal to 22.5 mm plus 22.40 mm. Therefore, total delta becomes 24.9 mm. So our deflection limit is that. So from the code book, we will check, since we have so far we have discussed that only point load. So we have to check for our UDL also. So if it is combined together, then delta will be span divided by 300. So span is 10,000 divided by 300. So 10,000 divided by 300 becomes 33.33 mm. 33.33 mm. So delta will be 24.9. So limiting value is delta limiting is equal to 33.33 mm. So hence the deflection is in safe criteria, hence safe in deflection also. Okay. So as per if we are going with the section IS WB 600, then all the criteria like our moment transfer will be safe, then shear transfer will be safe. So then after deflection criteria also will be safe. Okay. Hence the section is satisfying all the requirements. Still we have to do web buckling and web crippling. But the thing is, in the question they didn't mention about checking of web. Okay, so simply we can leave right now. Okay, so only they have asked check for the section in shear and deflection. So those two things are satisfied. Okay, thank you.